a question about this exercise. So I don't know if you wanted me to ask you later, but I made a note because this is what actually gave me the solution. And this one I tried with the substitution, but I haven't get here. So I know there's something wrong. So I don't know if you'd be able to tell me, just because I'd like to not have to do that as well.
Okay, so we did a substitution, and you said there was another. You did the substitution, or the substitution didn't work out?
Yeah, so I did the substitution, but then when I worked it out, I got to this result, and if I plugged that back in, it didn't work. Whereas this way, I actually got to this function. When I substituted that into the initial function, that would actually work.
I see.
So I was expecting to see the same.
Right, right. Yeah, you should.
But it was just to let you know that this is the one that I'm submitting. And this way, if we had time, perhaps that would be even quick. No.
Yeah. Yeah, or
was your in office hours?
After class.
Yeah. Thank you.
You can hang around for a little bit then. No. Okay, welcome back. I want to remind everyone, I said this in class, I hope that everyone caught it, that last class I said that I was going to post a homework assignment after class that would be due today. And I have several sitting here, so apparently a lot of people caught it. If you didn't, if you could, it's actually quite short. If you could get it done and email it in by tomorrow night, I will accept it. If you turned in a partial paper because you didn't have time to get it all done, then email me the rest of by tomorrow night, and I will accept the remainder. So with that, we are ready to start with the next lesson. So okay, tonight we're going to be looking at a couple of things. We're going to be talking about exact differential equations and integrating factors. I actually started this last time, but I didn't do many examples, and I want to rectify that. And then we will be talking about first order linear differential equations. And there's another class of equations that are closely related to them called Bernoulli equations. So we'll be looking at that. In these, for these two sections tonight, it's actually probably just easier for me to write on plain paper rather than to fill in the blanks on the notes, because there aren't that many blanks in the notes. The notes, however, are intended to be useful as references. So what I want to do first is how we started last time. And what I want to do is start with a function of two variables, u of x and y. And this one is x plus x squared y cubed. And we'll set that equal to a constant. And this would be some kind of a surface. Since they're nice polynomial factors, it's a smooth surface. And we would like to we would like to specify some level curve on the surface. That's what this equals k does. And then were we to compute the differential of this function of two variables, we'd have, you take the partial of this function with respect to x, partial derivative, and multiply that by dx. And then the partial of this with respect to y. Multiply that by dy. And then the differential of a constant function is 0. So you end up with this. And this is, by construction, an example of an exact ordinary differential equation. An exact ordinary differential equation means that you have an equation that can be put in this form. The standard form, people usually say something like this: m dx plus n dy equals 0, where m is the partial derivative of u with respect to x, and n is the partial derivative of u with respect to y. So if you can do that, then then the solution of the ordinary differential equation is this right here: x plus x squared y cubed equals k, and that's an implicit solution. Of course, in this case, you can solve explicitly for y. Push the x to the other side, divide through by x squared, and take the cube root, and you're done. But that's what we mean by an exact differential equation. Now, if you just presented, let's take this one right here. Let's take that ODE one more step. We could solve for dy dx. And that would mean you push this dx term over to the other side, and then you divide through by the coefficient of dy. So you have minus the quantity 1 plus 2 xy cubed over 3x squared y squared. So if you were just to come across the differential equation in an application, it would probably be in this form here. So you got dy dx equals something, fairly complicated combination of x's and y's. The first method we used was separation, and you can see you can't separate this. You can't multiply this through by some factor that'll get the y's on one side and the x's on the other. So what do you do then in order to get back to this? Well, the answer is that you first check to see if it is exact. And what we're using is the fact that the two second order mixed partial derivatives are equal, to test whether those factors that occur there originate from the same u or not. So what you do is you take this m factor here, take m and compute its partial derivative with respect to y. We've got its partial with respect to x. So if we take its partial with respect to y, that would be the second order mixed partial. And that gives me well, derivative of x is 0, and derivative of y cubed is 3y squared. And if I take the partial derivative of n, this guy here, with respect to x, I get 6xy squared. And I don't get that. I get 6xy squared. Okay. And then you notice that those are equal, and therefore this equation is exact. Now, normally you don't have this line here, right? So in this case, we started with the u, so of course we knew it was exact when we started. But normally you'd start either at this line 1 or at this line 2. And if you started at 2, then your first step would be to put it in this form here for line 1, and then you would do this check and find out that it's exact. Once we know it's exact, then we can solve it by the methods of for exact equations. So u of x and y is equal to, because I know it's exact, I can move forward with this. I can take the antiderivative of this first term, 1 plus 2xy cubed with respect to x. In other words, this is the partial with respect to x. We'll just undo that. So I get x plus taking antiderivative of 2x with respect to x, I get x squared. And then when I take the antiderivative with respect to x, you could get another term, there could be another term there that's constant with respect to x. And that means, of course, any function of y or just constants alone, you don't know which. But once you have this, so that's the general form of u. And by the way, we know what u is. We can look at it, right? So we know ahead of time that term is just, it's 0. But now take the partial of u with respect to y, and you get 0 for this term, plus 3x squared y squared. And then you match it up to, let's see, you match it up to this one here. And in this case, those match up perfectly. Oh, and I forgot to say here, plus, I was not looking at the right line. I'm supposed to be looking here. Take the derivative of this with respect to y. You do indeed get 0 plus 3x squared y squared. But then when you take the derivative of g of y, you get g prime of y. And this one does not have another term to match. So that tells us that g prime is equal to 0. So g is just a constant function. I won't even bother to name it because it's not important. That means that the solution to the ODE is u equals a constant. Well, let me, in this case, say K1, and then I'll write down what u is. We just computed u. It is this thing right here, except we've now discovered that this g is just a 0 or a constant. And the constant doesn't matter. So I'm going to write it out one time with the constant, but then you'll see it doesn't matter. What I know is it has no x's and y's in it, and that's what matters. So I could say this is some constant plus some constant is equal to K1, but then I would take this constant and subtract it from that side, and I have x plus, where is it? Right here. I looked at the wrong. Right here. 3. I'm still looking at the wrong line. Let's just scrap that and try again. Right here is my formula for u, right? So u equals x plus x squared y cubed plus g of y. I found out that g of y is a constant. So if you wanted to not write 0, but to be really careful, you could say there's some constant in there, perhaps, might be 0, but it also might not. And then that's equal to something, say K1. Well, now, when you simplify the next step, you get x plus x squared y cubed, subtract this constant from that constant, and you get another constant, which I'll call k. So you don't have to worry about just a constant on this step. It doesn't matter. It will just get absorbed in the constant on the other side of the equation. If you put it in, no one will be offended. If you skip it, no one will be offended. It doesn't matter. So here is the solution, the implicit solution to the ODE. Now, when we say an implicit solution, we mean this. There's some function of x that you could put in here, and it would make this work. And this describes its relationship with x and the constant. Now, we know in this case how to solve for y. And that's great. X squared y cubed equals k minus x, and then you divide through by the x squared, and then you could take the cube root. So there it is. Now we have an explicit solution to the ODE. Very often you cannot do this. The equation u equals a constant is so complex that you cannot solve for y. And if you can't, you just can't. You know, you just leave it at that and say, okay, that's the closest I can get to a solution. All right, any question about this so far?
Is this like the conservative vector fields?
Like vector fields?
Like conservative vector fields where the gradient is like or the two partial derivatives. And in order to find out if the field is conservative, you do kind of the same thing.
Oh, do you? Oh, I don't know about that. So I can't answer the question.
But yeah.
Okay. I mean, if you're starting with some kind of a nice function and you're taking partial derivatives, and I mean, there's obviously some connection, but whether it's exactly the same thing, I don't know. Okay, so I'm gonna redo this one. Only I'm gonna start right here. I'm going to do it another way. And a very different way. So here's the equation we want to work on. Now, what we did last time was this. We first of all decided that it was exact. And once we decided that, we said, well, if it's exact, then this is the partial derivative of u with respect to x. Take the antiderivative with respect to x, and you must have at least the general form of u. Well, you could argue in the same way for this one, right? You could say, if this is the partial derivative of u with respect to y, then u must be equal to an antiderivative of 3x squared y squared. This should be a y here. Right? Comes right from there. It should be an antiderivative with respect to y. Okay, well, if we take the antiderivative with respect to y, 3y squared has antiderivative y cubed. And then once again, there could possibly be a function of x alone, no y, because we've taken care of all the y's here. But maybe there could be a term involving x. So then you say, okay, the partial of u with respect to x then would be 2x y cubed plus f prime at x. And you match that up to your other expression for the partial of u with respect to x, which is 1 plus 2x y cubed. And you can see that, let's see, this term and this term match up. And therefore, f prime at x must be equal to 1, which tells me that f of x must be equal to x plus possibly a constant, but constants don't matter at this particular stage of this particular calculation. In general, they matter, but right now it doesn't. So that tells us u is equal to, what I'm doing is looking back at this form right here. U is equal to x squared y cubed plus f at x. But now I know that f is x plus perhaps a constant. And then I'm going to set the whole thing equal to a constant and say that's the solution to the ODE. So now we've done it twice. And what I'm trying to do is, by example, explain a few things here. Number one, just in general, what's the method? And the answer is check to make sure it's exact. If it is, then you could take the antiderivative of either one of these terms. It wouldn't matter. And by the way, they're already labeled for you with the dx and the dy. So, you just lift one of them up and stick an integral sign in front of it in terms of what you're writing. And then you find that antiderivative. Don't forget that terms that involve x alone would be invisible at this point. So you have to allow that they might be there. In the same way, when you take the antiderivative here, you might possibly have terms involving only y. They would be invisible because this is the derivative with respect to y. So with respect to x. So anything involving only y would just be wiped out to 0 when you take the partial. So you allow for that. And then in this case, we actually got something. It was an x. So we put it onto this part that we got way back here. There it is. Put on the x, set it equal to constant, and that's the implicit solution to the differential equation. And they should be the same, or at least equivalent, right? So are they? This one is x plus x squared y cubed is a constant, and I just wrote them in the other order here. So yes, they're equivalent. All right. So as long as the integrations aren't too hard, generally speaking, this is not that bad. So let's do one in its full glory now, without so much explanation. We'll just do the calculation. Okay, so our differential equation starts here. And of course, generally speaking, what you want to do is think of the easiest methods and then start ratcheting up to those that are more and more challenging to solve your ordinary differential equation. Now, right now, we only have two systematic methods, separation and exact equations. So you look at this and say, well, could I possibly separate it? The answer is no. I could do a little bit of factoring in the numerator and denominator, but not enough stuff cancels out to be able to get x's on one side and y's on the other. So that means I could try to see if it is exact. That's the next step. So I'm just going to cross multiply, basically. It's this times this, so, and this times this. So I've got minus x cubed plus 3xy squared dx is equal to 3x squared y plus y cubed times dy. And then if I say add this left side to the right side, then I'll have 0 is equal to, it'd be that plus that. So x cubed plus 3x y squared dx plus 3x squared y plus y cubed dy is equal to 0. All right, and the reason I need to do this is it needs to be in standard form. Before I do the check for exactness. If I took like the partial of this with respect to y and the partial of this with respect to x, they would not be equal. And it wouldn't mean that this is not an exact equation because I didn't start in standard form. So look at this one and say, okay, what we're hoping is that this is the partial of u with respect to x. Let's take its partial with respect to y. And we get 3x squared, whoops, with respect to y. We get 0 plus 6xy. And likewise, take the partial with respect to x of this factor up here, 3x squared y plus y cubed. And we get 6xy. Um, 6xy and 0, right? This has only y's in it, so partial with respect to x is 0. Those are equal, therefore it is exact. Okay, so that means I should take the antiderivative of either this piece here, write an integral sign in front of that, or write an integral sign in front of this. Either one of them will give you the general form of u. So I don't see any reason to prefer either one. So I'll take the left one, but there's no good reason for it. I have to choose. So I'm choosing the one on the left. All right, antiderivative with respect to x. I get x to the 4 over 4 for the first term, and 3x squared y squared over 2 for the second term. And it could possibly be that the original function u had some terms involving only y. If they did, once I had taken the partial with respect to x, which is that part right there, the y terms would be all gone. So I just have to say, maybe there are some y terms I don't know or not right now. I'm allowing for the possibility. Okay, then the partial of u with respect to y, that is this right here, right? So, but we can also get it from here. So we're going to compute it two ways and match them up. So taking the partial of this with respect to y, well, this term has no y's in it, so its partial is 0. This term has a y squared, so partial with respect to y of just that factor is 2y, so we get 3x squared y plus the derivative of any pure y terms. And that we match up to our other expression for the partial with respect to y, which is that right there. And in this form, we can see that the 3x squared y's, those match up, but y cubed, that must be equal to g prime. So those terms would be y to the 4th over 4. Therefore, u equals, okay, I got to go all the way back. Here's our general form for u right here. U is equal to this. So we know now that u looks like this: x to the 4 over 4 plus 3 halves x squared y squared plus g of y, but g of y, we have now discovered its y terms are y to the 4 over 4. There may be a plus c But it doesn't matter if there's a plus C because we're going to set this equal to a constant. This right here is the solution to the ODE. It's the implicit solution to the ODE. Okay, now I know from experience that for most people, it takes a few passes to catch on to the pattern here. Because it's fairly, I mean, each individual step isn't that hard, but you know, the pattern is not trivial. There's multiple pieces to it. So let me just ask, at this point, does it make sense? Can you look through the calculation and say, oh, I understand why he did this, and oh, sure enough, they're equal. Does it all make sense, or is it a little foggy yet? Okay. In that case, off camera, I'm going to select a U. And I hope I don't botch it up in the translation. So, since I started with the answer, I pretty much need to copy it. Now, this is one of those places where the advantages of being on site are pretty evident, because what I would encourage you to do is to see if you can work this one and compare with someone. Oh, good. I got back to the thing I started. Now, if you're watching online, there's no reason you can't text somebody, somebody else in the class. And once you get to the point where either you think you have a solution or you just don't know what to do next, then it would be wise to check with someone else and see if you have consistent results. Got a solution? Interrupted. You could check with Jorge, he's right behind you. Oh, I thought you were done. Sorry. Looks like maybe those guys got some. Okay, here is what I have. And of course, I had a distinct advantage of having the answer. You know, I made that up in the first place. And I just try to get something that would have a little interest to it, but wouldn't be too messy to work out. So I took the partial of that times dx, partial with respect to x times dx, and partial of that with respect to y times dy. That's the equation. And then I took the antiderivative of this term here. Of course, you could have started with this one. That would be fine. They're equivalent. So, I mean, those are equivalent methods. So take the antiderivative, I got this. And then I took the partial of this with respect to y and matched it up to this piece. So 3x squared y squared plus 0 plus g prime y equals this piece here. And that tells me g prime is 3y squared. So g must be y cubed. And then I take this, which I had before, and throw on the y cubed for g of y and set it equal to a constant. Okay, any questions now? One of the challenges in learning is, first of all, just discovering what your questions are, right? On things like this, it's easy to sort of nod and say, oh yeah, I see. But then when you're just sitting there with a blank piece of paper with one equation on it, that's a whole different game, right? So, so that's why I like to pause a little bit. And if we had more time, I would pause a lot more. Okay, let's take a look at this one. And this one is important, even though it's quite simple. It's important for a couple of different reasons. So this looks pretty simple. Seems like we ought to be able to knock out the solution quite quickly. And I'm making a mistake here. Okay, but we'll come back to identify the mistake in a moment. And I'll say, all right, U is equal to, let's see, the antiderivative of minus Y with respect to X. And this is equal to, let's see, minus YX plus possibly terms involving only Y's and constants. Then the partial of U with respect to Y is minus X plus G of Y, G prime of Y rather. And I match that up to the other term, equals X. And I think, I got a problem, right? Because if I solve this thing for G of Y, G prime at Y, it tells me that's equal to minus 2x, or rather to plus 2x. I add x to both sides, which is impossible. This is supposed to be a function of only involving y, not involving x. So, big problem. You already know where the mistake is. What's the mistake? I omitted something. I failed to check for exactness. So what's supposed to happen here all right, so let's do that. I'll take the partial of this minus y. Now here, if this were exact, this is already a partial with respect to x. So now I'll take its partial with respect to y. I get minus 1. And on the other one, I take the partial of x with respect to x, and I get plus 1. And these are not equal, so this is not exact. Therefore, plowing ahead with the methods for exact equations will hopefully generate a contradiction, so you'll know something is wrong. But who knows? You know, maybe it won't, and you'll just plain get the wrong answer. Point number 1 from this example is do not forget to do the check to see if you have an exact equation. If you don't have an exact equation, don't use the methods for exact equations. Now, point number 2 is this. This is actually an incredibly simple equation. Let's see, we could write it this way. X dy equals, I'm going to put that on the other side, y dx. I'm going to divide each side by dx. And I'm going to divide each side by y. And actually, I probably shouldn't have done that. Leave that where it was. And I'm going to multiply, I'm going to divide each side by x. So 1 over y dy equals 1 over x dx. We can integrate, and we get the natural log of absolute value of y equals natural log absolute value of x, perhaps plus some non-zero constant. And this, by the way, could itself be a log, right? So that would be the log of some other constant times x, and therefore y equals plus or minus c2x, and that's the general solution. It's easily obtained from separation. You don't have to go through all the trouble of using the methods of exact differential equations. So, so the second thing I want to emphasize here is try the easy way out first. The only two methods we have right now are separation and exact differential equations, and separation is generally easier. So, try the easiest thing first. Now, the third thing I would like you to see is let's go ahead and start back at this original equation right here. And I'm going to divide this by x squared. So I'll have minus y over x squared plus 1 over x. Oops, I forgot my dx here. Dx plus 1 over x dy equals 0. And I got to change this anyway, so I may as well recopy that and make it closer to legible. Y over x squared dx plus 1 over x dy equals 0. Now, of course, this is still separable, but nevertheless, let's see what we could do with this. Let's see if this one is exact. I'm going to take the partial with respect to y of y over x squared. And if I do that, let's see, a little bit of a mistake here. Notice right here, it's got a negative sign. You can't see that. It has a negative sign, and when I copied it, I left the minus sign behind. So put that back in. Okay, so take the partial of this with respect to y, and you get minus 1 over x squared. And now I'm going to take the partial of this with respect to x. Well, this is x to the minus 1, and its derivative with respect to x is minus 1 x to the minus 2. Aha! Now it is exact. So what that means is equations can flip-flop between being exact or not exact by multiplying or dividing by some factor. It turns out that this one is particularly amenable to being, well, we started way back where? Oh, right here. We started way back here. That equation is particularly amenable to being converted to an exact equation. If you divide it through by x squared, it becomes exact. If you divide it by y squared, it becomes exact. If you divide it by x times y, it becomes exact. If you divide it by the sum, x squared plus y squared, it becomes exact. If you divide it through by the sine of x, it's not exact. I didn't want you to think anything would work. So this thing can be converted, this original one could be converted to an exact equation. And if there is a factor you can multiply through by to turn a non-exact equation into exact, we call it an integrating factor. And a careful statement of that is in the notes you can grab off from Blackboard. But for now, we know if you can multiply through by something and turn the non-exact equation into exact, we call that factor an integrating factor. So it would be nice sometimes if we start with a non-exact equation, if we could figure out how to come up with an integrating factor, right? So that's sort of the second level of working with exact equations. Number one, just get it in the standard form and check it. If it's already exact, well, use the methods for exact equations. Level two, it's not exact, but it looks like maybe you could come up with a relatively simple integrating factor. Well, then go get one and multiply through by the integrating factor and then solve the equation. So how do you know if there is one? And how do you find them if there is? And that's the next level for this. So what I want to do now is, in general, people like to write this. or at least Kreyszig certainly likes it, m dx plus n dy equals 0 is exact if partial of m with respect to y is the partial of n with respect to x. Now, let's take a different equation, and I'll call this p. So it's p of x and y. This is a function. P of x and y dx plus q of x and y dy equals 0. Let's suppose that thing is not exact. But there's some factor f, and this may be a function of both x and y again, that if you multiply through by f, the new equation is exact. So what that's saying is that f is an integrating factor. So what we're trying to do is come up with a formula that would spit out integrating factors, or at least tell us that we can't get one. Okay, well, let's suppose now that this f really is an integrating factor. Then this equation that I have written down here is exact, which means that if I take the partial derivative of f times p with respect to y, I get the same thing as if I take the partial of f times q with respect to x. So let's say that with equations. Partial with respect to y of fp must be the same as partial with respect to x of fq. Oh, okay, well, I guess since these are products, we better use the product rule. So taking the partial of this product with respect to y, I get a partial derivative with respect to y. I'm going to use the shorter notation, f sub y times p plus f times p sub y equals, same notation over here, take the partial derivative with respect to x, fxq plus fqx. And what I have done is converted my relatively simple ordinary differential equation. Now these are partial derivatives, right? I had two terms in my ODE, and now I've got partial derivatives in 4 terms. Not better. However, sometimes you can make an assumption that will simplify things. So this is too complex for the case when f is a function of both x and y. Now you might be able to make some headway in some cases, but in general, it's just, we're not there. This is not the sort of thing we're working on, it's too hard. But what we could say is this, we could try 2 special cases. What if f were a function of x alone? So in other words, there's no y's in the formula for f. Then the partial derivative of f with respect to y would be 0 because it has no y terms. So this would simplify quite a bit. This first term here would drop out. I get 0 plus f times, let's write it out now, partial of p with respect to y equals, and the partial of f with respect to x, it's just an ordinary derivative because there aren't 2 variables in there. There's just x. So that's f prime of x times q plus f of x times the partial of q with respect to x. Now that might not look a whole lot better, but in some cases it really is. So what I'm going to do now is try to solve this thing for f. So I've got, let's see, I've got an f on this term and on this term. So I'm going to put those together. F prime of x times q of x and y equals f of x times partial q with respect to x minus, this term here goes to the other side of the equation, minus f of x times partial p with respect to y. I can factor off the f, and I get in the brackets partial q with respect to x minus partial p with respect to y. And then I can take this equation right here, f prime q equals this stuff. I'm going to divide each side by f.
I have a question.
Uh-huh.
Why is dq dx minus dp dy? Right there. Shouldn't it be dp dy minus dq dx?
Okay, what I'm going to do is, it should, I think you're right. No, careful. F is here and here. Yeah, this one moves to that side. So partial p with respect to y minus partial q with respect to x. Let's see what I got last time I did this. This is very finicky in the end. That's why I want to be careful.
Right.
So thank you for asking. P with respect to y. Yes. As the French say, touché. Okay, let's get it right. All right, so I am trying to solve right now for this guy, f prime at x times q equals, then I have that on the other side, f partial p with respect to y minus, this goes over there, f times partial q with respect to x. Okay, and now back to work. We have 1 over f. I'm dividing each side by f. This I'm going to write as df dx equals, and now I'm going to divide each side by q. Partial p with respect to y minus partial q with respect to x. All right, now, how would you know whether this, if this thing were going to work? Because remember, it's based on an extra assumption, right? We're assuming back here that f is a function of x alone. Well, if that were true, then the only thing I have on the left-hand side is x's, right? You start with a function of x alone, that's the 1 over f, and then you take its derivative. Well, you can't produce a y that wasn't there before by taking a derivative with respect to x. So this would have only x's, and so this right-hand side would have to have only x's. And furthermore, this is a differential equation for f. So not only does the right-hand side have to have only x's, we have to be able to solve the differential equation. So we're solving a differential equation to find an integrating factor so that we can solve a differential equation, just to be clear. There's 2 equations, right? So, and we can compute f from this ODE. Now, if you make the opposite assumption, you could assume that f is a function of y alone. If you do that, then you'll get a similar formula. If f is a function of y alone, then 1 over f df dy equals, I think this one goes to 1 over p. Yes. 1 over p partial of q with respect to x minus partial of p with respect to y. These two flip. And I'm actually looking on my notes here, so I'm not just, listening to the universe and it's telling me. No. I computed it with great care this afternoon, and then I looked it up in my copy of Kreutzig because I didn't want to tell you the wrong formula. And I nearly did anyway. Okay, so if there is a integrating factor that is a function of x alone, then it will satisfy this first equation. And perhaps I can figure it out from this. If there is a function of y alone that's an integrating factor, it will satisfy this second equation, and I may be able to solve this ODE to find an integrating factor with respect to y. So maybe just for an example, why don't we see what happens here? Let's take this equation that we started with, a long way back. I think it was this, minus y dx plus x dy equals 0. And we checked that to see if it was exact, and it failed. So if we take the partial with respect to y, we get -1. Take the partial with respect to x, you get +1. It failed. It's not exact. Does it have an integrating factor? F, which is a function only of x? That's the question we're asking. And I don't know if this is going to come out nicely or not. I did not do this ahead of time. But we have a formula. If so, the F should satisfy this equation. And these are things we can do. F is an unknown function, of course. So I'm working on that. So there's no translation there. But the P and the Q, we can say this is P and this is Q. So 1 over Q is 1 over X. Partial of P with respect to Y, -1. Minus partial of Q with respect to X, +1. So this gives me -2x to the -1. And that is the derivative of F. So antiderivative 1 over F dF equals antiderivative of -2x to the -1 dx. And let's see, this is log of absolute F equals -2 log of absolute X plus perhaps a constant. But this is going to be another one of those cases where constants don't really matter. So then you take the exponential of both sides and you end up with this. F is equal to, oh, now I should mention this. This -2, we can use properties of logarithms to write that as an exponent, right? Log of x to the -2 in absolute value plus some constant. So now you take the exponential of both sides and you get e to the log of x to the -2. That's just x to the -2 plus c1. But when you add exponents, that's the same as multiplying with like bases. And so simplifying that whole mess, e to the c1, e to a constant is a constant. And this is e to the log of x to the -2. Well, that's x to the -2. Or any constant over x squared is an integrating factor. But we already checked that out, right? We did that earlier. So this then becomes an example of computing an integrating factor. And I've got a fair amount of mileage out of that one simple equation, right? First thing is this, always check, if you're going to use methods for exact equations, don't forget to do the check. Number two, try the easiest methods first. Number three, there may be an integrating factor. In fact, we computed ahead of time. We know that 1 over x squared is 1, but then we generated these formulas. We tried the first one, and in this case, we're lucky enough that it actually gave us a simple integrating factor. And since we've already tried this, we know ahead of time. We did it before. If you take this equation and divide it through by x squared, so you get minus y over x plus 1 over x dy, that is indeed exact, and you can solve the equation in that way.
So after you've solved for u using the integrating factor, do you then have to get rid of the factor to get the actual u?
No, no, that's a simple answer. If you, let's see, we did that right once. Okay, so I took this one here, original, I divided it through by x squared. Did I not solve it then? Looks like I didn't. Okay, so if I take the partial, well, this is now exact. I think I did check that, didn't I?
Mm-hmm.
Okay, so if we wanted to solve this equation, I would probably work with this one. That's a little bit nicer. U is equal to the antiderivative of 1 over x dy. So let's see, we've got 1 over x is constant with respect to y, and this gives us a factor of y. So partial u with respect to x is minus y over x squared. And you set it equal to this one. Oh, plus possibly terms involving only x. And you set that equal to this one. So you see that that's a derivative there. F prime is equal to 0. So those missing terms, if there are any, they're just constants. And therefore, that gives me this solution here. Where is u? Here's u. Y over x equals a constant. And I think we solved it by separation and got the equivalent solution. But I don't even know where I put that. You think you have a hard time with my notes. I have a worse time. I have no idea where it is. But I remember doing it. So those pieces get used up in the integrations and differentiations, and everything comes out in the wash.
So the factor just kind of cancels itself out once you go through everything?
Well, we actually needed it in order to do the method. So in a certain way, yes, but in another way, no. It becomes part of the method. Okay, so anyway, it's a good question. Another way of thinking about that is this. We started with this, p dx plus q dy equals 0. And then suppose we multiplied it through by an f. If you solve this for dy dx, in this form, the f would cancel out because you put this on the other side, minus fp dx, divide through by the dx, and then divide through by the fq, and sure enough, the f's go away. So in the derivative, they do cancel out. Okay, so those are integrating factors, and I would love to do more I think I would love to do more, but I can't. We have to move on. So let's, I don't know, let's take about a 5-minute break, and let's see. It's 7:09 now, so at 7:13 by the computer clock, we'll reconvene. You all are so different from the last group I taught. If I was 2 minutes late on a break, oh, get antsy. As soon as I said, okay, let's take a break. Whoosh. I got a part-time job this summer, emerging from temporarily, I guess, from retirement. And it is so cool. This company has this big database program, which is, as it turns out, completely obsolete. And so there is absolutely zero documentation available for it. The company that sold it is still in business, but they won't service it. And there are, I don't know, 4 or 5 different databases that run under this engine over the top, and they need their data out. They said, can you recover our data? I said, well, actually, I've never even taken a course in database, so I don't know. I said, what you need is an expert in databases. I said, correct, but we can't afford one. Would you try? So I started on one of the many databases last week or the week before. And databases are kind of laid out, the tables, like sort of like spreadsheets. And rough numbers is around 100 different tables and around 8,000 different columns. But the nice thing is they want me to hack it. So, I don't have to avoid security. And I'm starting to make progress. And I pulled some stuff out now, but there's a lot to go. But now I found out that the databases are not standalone. I found this out yesterday. Sometimes a query goes over here to get stuff to do things over here. Oh no, that's worse than I thought. But it's fascinating. It's kind of a lot like doing being a research mathematician. It's just this cloud of mysteries, and you just get little hints here and there. Hack away at it. That might be a great career. Too late for me. Mine's already done. But okay, I said we were going to restart, so we should. Well, I think I should abandon any further hope of talking about. But there was one that's really kind of important. Okay, let me tell you a little bit. I'm not going to put this in the context of a differential equation, but you need to know about these functions because they come up in, no, not these. I'm assuming you know these. This is the analogy I'm going to draw. You know about sine, cosine, tangent. There's some similar functions that are defined, and if you're working in science and engineering, you might very well have come across them already. However, I know that in the mathematics curriculum, it is not at all uncommon that the first time someone encounters the hyperbolic functions is in differential equations. So if that's you, I am trying to give you a little help about what the hyperbolic functions are. So SINH is officially the hyperbolic sign, and that's e to the x minus e to the minus x over 2. Its graph is sort of kind of like this. The hyperbolic cosine, get that on camera, there we go, is e to the x plus e to the minus x over 2. And its graph is like this. Well, it's supposed to be symmetric. The one side is supposed to be a mirror image of the other. And furthermore, its y-intercept is 1, and that one has y-intercept 0. And so in some ways, these are kind of like the sine and the cosine. The hyperbolic sine is an odd function. Sine of minus x is minus, I should say, hyperbolic sine of minus x is minus hyperbolic sine of x. And the hyperbolic cosine is even. If you replace x by minus x, you get the same function back. Also, like cosine, the hyperbolic cosine of 0 is 1, just like the cosine of 0 is 1. And the hyperbolic sine of 0 is 0, just like the sine of 0 is 0. And we define the hyperbolic tangent to be, well, you could write it out in terms of the exponential functions if you want, but it's just hyperbolic sine over hyperbolic cosine. Now, these actually come up quite often in applications of differential equations. And I know they come up in engineering because, not because I know anything about engineering, but because I have an engineering math book. And when I work on problems out of that, hyperbolic sine, hyperbolic cosine, hyperbolic tangent are not uncommon functions to encounter. Something that, a couple of things you should know. First of all is how people pronounce these. This is usually pronounced sinh of x. And that as cosh of x. At least that's the version I was taught. Okay, so now it wasn't too long ago I was teaching this course and talking about homogeneous systems of equations, and someone corrected me and said it's homogeneous. Well, back when I was a student, it was pronounced homogeneous. So you can say it either way, I don't care. But I was taught to pronounce this because hyperbolic sign is kind of a mouthful, right? So people say sinh of x and cosh of x. I do not know of a short version of hyperbolic tangent. I don't know what we'd say, tan of x. Doesn't really work in English. Some languages have this, like Greek has a rough breathing. I think there's some consonant in Spanish, is there that it's some kind of sound like that? So I don't know. Yeah, yeah. So maybe you could say, I don't know. Tan hey. I'm not sure. So anyway, I'm just telling you, these are the functions. They're, you know, if you want to get a picture of them on your calculator, you can. It's just e to the x minus e to the minus x over 2. Graph that, and you'll have a graph of sinh. So don't be stunned if these pop up in the problems. And if you do see them, you can always switch back to the exponential form. But there's something you probably will like about them, and that is if you take the derivative of the sinh, you get the cosh. Now, that's just like, well, it's sine and cosine, right? Take the derivative of sine, you get cosine. But this one is a little bit nicer than the trig function. If you take the derivative of the cosh, you get the sinh, not negative sinh. So that agony you went through in calculus 1, where it said derivative of the sine is cosine, derivative of cosine is minus sine. And you drilled that over and over and over and over and thought, this is so complicated, I will never learn it. Only to decide the next semester, gosh, I wish we could go back to things that were that simple. Well, here you can just forget all about that minus sign pattern. It just doesn't happen, okay? And if you check out the other derivatives, things go along looking pretty much like the trig functions, but not exactly. Okay, I want to tell you a little bit about first order linear differential equations. And in the notes, I don't think I did on this one, but I could have. I oftentimes put a little section in this part of the course anyway called a quick start. And so this is the quick start for first order linear ordinary differential equations. If you have one, it looks like that. So for instance, you could have this, y prime plus 3 over xy equals, what would be nice here? E to the 2x probably is not too bad. You know, 1. I want to make sure I get one that I can solve easily. The solution to this, there is simply a formula. It's e to the minus h times the antiderivative of e to the h r dx plus c inside the parentheses. So it's e to the minus h times c, where h is an integral of p. So in this little example here, which I do hope doesn't turn out to be hard, you would say h is an antiderivative of p, the coefficient on y, and you could put in the absolute values and the constants, but they won't matter. So y is e to the minus h. Now, this is log of x cubed, right? So e to the power minus log of x cubed times integral e to the h, e to the log of x cubed times r dx plus c. And okay, this, put the minus sign up here with that 3. So this is e to the log of x to the minus 3. X to the minus 3. In here, you don't have the minus sign, so e to the log of x cubed is x cubed. So it's x to the minus 3 times, okay, antiderivative of x to the third is x to the 4 over 4. And distributing the x to the minus 3, we get x over 4 plus c x to the minus 3. And I think it might even work. It does. Cool. All right, so sorry, I got excited there. So y equals x to the 4 plus cx to the minus 3, y prime equals 1/4 minus 3c x to the minus 4. Now, if you plug it back into the original equation, which is somewhere right there, way up there. So y prime plus 3 over x y is equal to, y prime is right here, 1/4 minus 3c x to the minus 4. That's y prime plus 3 over x times y, and y is right here. X over 4 plus c e to the minus, not e, c x to the minus 3. And you get, okay, we've got a 1/4 here. And from this term, those two multiplied together give us 3/4. And then we have minus 3c x to the minus 4 here. And when you multiply 3 over x times this term, you get plus 3c x to the minus 4. So those add out, and you get 1 as advertised. Therefore, in principle, if you have any first order linear ordinary differential equation, you can solve it because the solution is sitting right here. You just do that. Now, that doesn't mean you'll be able to evaluate the integrals. The h, after all, is defined in terms of an integral. And even if you can find h, doesn't mean that you can do this, right? But at least you could write it down in terms of integrals. So that far, it is possible. It's possible to get that far with the solution. And it turns out that oftentimes in applications, that's actually good enough. So, you know, it would take some time to explain why, but it's true. Oftentimes that will bail you out of your difficulties. So we have done one of these. So how about if we How about if we do one more? Okay, I kind of like, ooh, that's maybe a lot for the next one. So let me do this one, y prime minus y equals e to the 2x. Now, maybe I really shouldn't even start it that way. I'm going to rewrite this, obfuscate it. So let's suppose we started here. Now, the first thing you must always do is put this in standard form. And this is one of those things that used to trip me up once in a while. Probably still does, but I think when I was first starting, because I thought, well, gosh, it seems like the equations are all equivalent. The formula should work no matter what. Yeah, but remember, we get that P of X and R of X out of the standard form. So if you don't have things on the right side of the equation, you could very well have a minus sign here. Or if you need to divide out an X or something like that, you could have a factor of an X in the way and things like that. So the standard form is this, y prime with a coefficient of 1. Then whatever coefficient you get, in this case, -1 times y, and then solved for the pure X terms and or constants on the other side. So this is P of X, and this is R of X. This is actually completely standard notation. The R here, when you see what people do when they go up to second order, you realize, oh, R means right-hand side, okay? There is a second order version of this, y double prime plus P of X y prime, and you don't need to copy this right now. We'll get to it later. But just by comparison, when people write this out, they still put R of X on the right-hand side. It means the right-hand side of the equation. And these special versions of that are really fun. Part of my favorite parts of the course. And we're coming up. It's like next week, I think we do some of that. So, okay, so if we wanted to solve that, we would say, well, fortunately, we have a formula. It's e to the minus h times integral e to the h r of x dx plus c, where h is an antiderivative of p. And p, in the standard form, is the coefficient on y. So in our particular case, it's the antiderivative or an antiderivative, it doesn't matter which one, of -1, which negative x will do. So y is equal to e to the minus x, antiderivative e to the h, which is minus x, r of x. R of x is e to the 2x dx plus c. Okay, e to the 2x times e to the minus x is e to the 1x. And fortunately, that antiderivative is particularly easy. So we get e to the 2x plus c e to the x. And that is the solution to the original differential equation, which I'll rewrite here, just so we can get it all on screen. Now, there's something useful to be seen here. Let me see. Yeah, first of all, notice if you just picked out the first term, e to the 2x, if you feed that through the left-hand side, you get the right-hand side. The derivative of e to the 2x you get a chain rule factor of 2. So it's 2e to the 2x minus e to the 2x, 2e to the 2x minus 1e to the 2x is 1e to the 2x. It satisfies the right-hand side. So what's this piece doing on here? Well, that's a solution to the homogeneous equation, or if you prefer, the homogeneous. Take e to the x and feed it in here. You get e to the x minus e to the x is 0. So this solves the homogeneous equation. Some people call it the homogeneous solution. This solves the solution with the non-zero right, is a solution to the equation with a non-zero right-hand side. And you put them together, you get all possible solutions. So it's the general solution to the original differential equation. And it's this C that really allows us to solve initial value problems. So suppose that we had an initial condition. Suppose, for instance, y at 0 is known and, I don't know, equals 5. Well, then you would plug the 0 in to this general solution. You'd have e to the 2 times 0 plus c e to the 0. E to the 0 is 1, so that's 1 plus c equals 5, so c must be equal to 4. And therefore, the particular solution, the solution that satisfies the original differential equation and meets the initial condition, is e to the 2x plus 4 e to the x. Now, there is a reason that this solves the equation. And if I had more time, I would tell you, but I don't. I did tell you in the printed notes. If you, of course, they're printed only when you print them. So if you download them from Blackboard and read them on screen or print them out, you'll see a derivation of this formula. But I would. I don't have a lot of time left, and I would like to use it to push a little further into examples. And there's one more class of equations that comes after this. Okay, so what we have now is this, sort of in summary, and it's in summary of all of differential equations so far for us. If you can get to this, g of y dy equals f of x dx. Those kinds of equations are what we call separable. And you solve them by integrating. That was the first thing we did. The second thing was this. We said, well, sometimes you may start out in this kind of a form here. Let's see, what does it turn out to be? I think that, because this will then reduce to minus m dx equals n dy, which is equivalent to m dx plus n dy equals 0, where partial of u with respect to x is m, and partial of u with respect to x is n, then we say that this is an exact equation. And we have means for doing that. And this is not coming out nearly so neat as I had hoped. Case 1, your equation could possibly be separable. Case 2, you get around to something which you can recognize as exact. Case 3, you can make it exact by multiplying by an integrating factor. If there is one, and that factor is a function of x alone, then 1 over f df dx is equal to, and now I'm feeling cautious since I got this wrong once. 1 over f df dx is 1 over p, 1 over q, partial of p with respect to y minus partial q with respect to x. And if it's a function of y alone, it satisfies this. 1 over p, partial q with respect to y, minus partial p with respect to x. Okay, third possibility. Your equation is in this form: y prime plus p of xy equals r of x. If so, you have a first order linear, and there's a formula for the solution, a very rare case in differential equations, but in this case there is one. E to the minus h times the quantity integral e to the hr dx plus c, where h is an antiderivative of p with respect to x. And the fourth case, which we're just now getting to, y prime plus p of xy equals r of x times y to the a power, where a is neither 0 nor 1. And in this case, you substitute u equals y to the 1 minus a, and the equation becomes linear in u. Solve for u, substitute back. To solve for y. And those are fine sounding words, but it would probably be helpful to see one of them, right? Oh, these have a name as well. These are called Bernoulli equations. Now, things don't all fall to pieces if you have y to the a, where a is 0 or 1. If a were 0, this would just be a 1 here, right? In which case you would have this equation right here. You'd have a first order linear. On the other hand, if this were y to the 1 power, then this term and this term could combine, and you'd have y prime plus some other coefficient times y equals 0. That would be a first order linear with a 0 right hand side, which is even easier than the standard one. So the reason we say a is not 0 or 1 here is not because it makes the equation unsolvable, but because it's already covered by case 3.
So there's only words with one more y variable.
Yes. Yeah. The only difference between the first order linear form and the Bernoulli form is that the Bernoulli form has a factor of y to the a power on the right-hand side. Now, I hear a hint in your question, which is, my goodness, these are really narrow, persnickety little classes of equations. And the answer to that is, you are exactly correct. Exactly. And that is both the beauty and the bane of differential equations, elementary differential equations, is there are certain classes of equations we know how to solve. And honestly, some of these methods work great. I mean, we just got a formula for first order linear. It doesn't get much better than that. You didn't even have that in Calc 2, right? Things were much harder. But if you fall outside of those classes, we don't know what to do, at least by the elementary methods. Now, there are some additional methods, and that's what part 3 of this course is about. You know, what do you do if you land outside of one of those standard techniques? Well, I'll show you some things, but to tell you the truth, what most practicing engineers do is they're gonna type it into a numerical solver. MATLAB has them, and you'll get a numerical solution. So that doesn't mean you shouldn't. At that point, then you think, oh, well, why don't we just dispense with this course? If we happen along across a differential equation, we'll type it into MATLAB and we'll get a numerical solution. Well, sometimes it's really quite nice to have the analytical form of the solution, which is the things we've been producing here. So it really is an advantage to know this stuff. And especially if you grind away for a few hours on your computer, only to find out that something like y equals x. You think, maybe I could have figured that one out on my own. Well, yes, you probably could have. So, of course, when you go further in differential equations, there's a bunch of what we call existence and uniqueness theorems. And they are just answering the question, does this equation have a solution at all? And if there is one, is there only one, or could there be a whole list of them? Well, there are conditions when you can figure that out. And that matters because if you, you tell the boss, gosh, I can't do this analytically, I'm afraid you're gonna have to ship it out. So he contracts with the Argonne National Lab for $500,000, and they grind away, and then they send back the bill and say, this doesn't have a solution. And you could have told by looking it up in the reference book, then, this is really not cool, right? So the analytical methods and the theory does have some utility. But there are cases where you just run out of gas with those, and you can't get what you need that way. That should not be a shock. Okay, I'm trying to find one of these that is non-trivial, but not beastly difficult. And I might not have actually, well, this one is not too awful. Let's do this one. Y prime minus AY equals minus B y squared. Now, A and B in this case, the problem says those are positive constants. So they're not functions, they're constants. And this is Bernoulli for sure. This one right here, y prime minus AY equals negative B, that would be first order linear, right? I get my hand out of the way, you can tell. It's y prime plus p of xy equals R of X. So it does fit the first order linear. And then if you take a first order linear and you multiply the right-hand side by y to the a, where a is not 0 or 1, you have a Bernoulli equation. So this is Bernoulli. Now the advice that comes with the formula for Bernoulli equation says this: set u equal to y to the 1 minus a, and all your problems will go away. Well, what does that mean? And now I'm going to try to show you what that means. It's actually okay. Oh, look at that off screen. Thank you. So in this case, we can see that a equals 2, where we have y to the second power here. So it's y to the 1 minus 2 power, or y to the minus 1. So u equals 1 over y. It's also true then that y is equal to 1 over u, or u to the minus 1. And therefore y prime is equal to minus 1 u to the minus 2 u prime. Okay, so let's make that substitution in the original equation. I want to be able to refer to that, so I'm going to call that equation 1. Substitute into equation 1, and you'll get minus 1 u to the minus 2 minus a y, but y is u to the minus 1, equals negative b y to the 2, which would be from this equation, y to the 2 is u to the minus 2. Okay, it would look like if we multiplied this thing through by u squared, it would sure help. Oh, I forgot the u prime. Right. See that right there? That goes in here. U prime. Okay, so multiply through, actually let's multiply through by negative u squared. So I have u prime is all that's left. If I hit that by a minus u squared, this would be minus a u, and this would be minus b. Plus b. The sign of everything's supposed to change. Minus, minus, minus becomes plus, plus, plus. Gosh, you can almost guess the answer to this. Let's try. U equals b over a. I think this is going to give me a particular solution. Okay. And I mean, these are constants, right? So it's just a number. Then u prime is 0. A times u would be b, and sure enough, I got b. Huh, this is a start. So I have a particular solution. Now I want the solution to the homogeneous equation. So I want u prime plus u to be equal to 0. How about this? AU. So when you take the derivative, you're going to get a chain rule factor, and it had better be a. But we need a negative, right? I think so. Double check that one. If I take the derivative here, I get minus a e to the minus ax plus a e to the minus ax equals 0. Perfect. So the general solution is b over a plus any constant times e to the minus ax. Now, if you don't like that method, which is stare at the equation and see if the answer jumps out at you, it's great when it works. if that doesn't happen, then of course you have to use a formula or a technique, right? So our first order linear form is y prime plus p of y equals r, and it has solution y, in this case u, equals e to the minus h. Well, h in this case is an antiderivative of ax, e to the minus h, there it is, times the antiderivative of e to the h times r dx plus c, which is, okay, this is constant b, comes to the outside of the integral. Antiderivative of e to the ax is 1 over a e to the ax. So I've got b over a e to the ax times e to the minus ax plus c e to the minus ax. Whew, equals, all right, those two things multiplied together to give 1. It's b over a plus c e to the minus ax. And I think, sure enough, excuse me for showing off, but I got something wrong earlier. So now I'd like to get something really extra right. And so they kind of cancel each other out. So I'll quit bragging now. Because I mean, unless I make another mistake, then I'll. Okay, but u, remember, u is something. We got that from a substitution. U is right here. U is equal to 1 over y. So you just take the reciprocal and you've got the solution. Y equals 1 over b over a plus any constant times e to the minus ax. So that's an example of a Bernoulli equation. So I have time to solve no more equations. Therefore, I will write down two that you can work on, but I want to give it with some hints. So you have a practice problem or two that this is not Bernoulli because it's, well, it just doesn't, it can't be made to fit into the form. So you've got a y in here. You have y prime times y. You need a left-hand side that's linear for Bernoulli. This is not Bernoulli, and it's not linear. The trick here is solve, just in, I don't mean solve a differential equation. I mean do high school algebra kind of solve for not dy over dx, but dx over dy. And take x to be a function of y rather than the other way around. And it will work. What you'll end up with in the end is this, y squared x minus hyperbolic cosine of 3y equals a constant. And my notes say, oh, it says, if it helps emotionally, it doesn't help mathematically. Set y equal to t. This is in terms of mathematics, this is a completely useless substitution, right? Everywhere it used to say y, make it t. But it will help you get over the hurdle of looking at this and saying, oh no, the y has to be the function. No, do it the other way around, and it comes out actually okay. So, and then at the last step, you switch them back. So give that a try. Here's another one. Y prime plus 2xy equals e to the 2x squared y cubed. This one is in fact Bernoulli. And the answer I got is e to the minus x squared over square root of c minus 2x. And my notes say it's kind of messy. So I got that, but not without some pain. Not a huge amount of pain, or I wouldn't have recommended it to you. So once you know it's Bernoulli, you're going to make a substitution. U equals y to the 1 minus a, right there. And that should turn it into a linear equation. Not an especially nice linear equation, but not horrible either. Can I get that on the screen? I guess so. Okay. That's it for tonight. And I am going to post a homework set to be handed in on Tuesday, and it will come up later tonight. And I just think if I were taking this course, these homework sets would probably feel like they were too many and too close together. I am so sorry, but it's a 4-hour class and we meet twice a week. And yeah, I don't have a better solution. Okay, class is over and office hours have started.